The universe is expanding, but here's the kicker. It's expanding into nothing. That's right, space itself is stretching at speeds that break all the rules, taking galaxies, stars, and everything else with it. And the craziest part, this expansion isn't pushing into anything else. There's no boundary, no outside for space to grow into, because space is all there is. Every second, the universe grows larger, and yet it's doing so into absolute nothingness. Now, think about this. Imagine standing in the middle of the universe, anywhere in the universe really, and looking around. Every galaxy, no matter where it is, seems to be rushing away from you. It's as though you're sitting at the center of it all, but so is every other galaxy. This might sound like the beginning of some mind-bending science fiction, but it's not. It's science fact. The very fabric of reality, the space that holds everything together, is stretching, and it's stretching in such a way that every galaxy feels like it's at the center. This isn't an illusion. It's a feature of the way space expands. This expansion, known as intrinsic expansion, started over 13.8 billion years ago with an event we now call the Big Bang. But don't let the name fool you. There was no explosion, no blast from a single point. Space itself began to stretch, and it's still stretching today. But while we can measure this expansion, grasping how or why it happens is another story altogether. The forces at work in the cosmos are not just huge, they're terrifying. There's an invisible force making up 70% of the universe, a force that's responsible for pulling everything apart, even as it shatters the very laws of physics we thought we knew. If you think you understand space, get ready for a complete rethinking of everything. The universe is stranger, more chaotic, and far more mysterious than anyone could have ever imagined. Stick with us, and we'll explore just how mind-blowing this cosmic reality really is. And trust me, it's going to leave you questioning everything you thought you knew about the universe. Space is not empty. Sure, when you look out at the night sky, all you see are stars, galaxies, and blackness in between. But the truth is, the vast, seemingly empty spaces between stars, galaxies, and everything else isn't nothingness. It's a stage where the most unbelievable cosmic events take place. Imagine this. The space between galaxies is constantly stretching, pulling galaxies farther apart. The vast voids aren't empty, they're teeming with an energy that pushes everything apart, making the universe expand at a relentless pace. Now, let's get one thing straight. The concept of space itself expanding goes against everything we intuitively know about the world around us. We are used to thinking about space as a backdrop, something that holds objects in place, not something that grows. When you think of an object expanding, you picture something pushing outward into a bigger space. Like blowing air into a balloon, it inflates into the surrounding air. But the universe doesn't do that. There's no surrounding space for it to expand into. The entire fabric of space is growing, and it's growing into nothing. This strange behavior of the cosmos is what makes the universe so mind-bending. To really understand this, we need to break it down. Think of a balloon. When you blow air into a balloon, you see the rubber stretch. It inflates into the air around it. If you could somehow live on the surface of that balloon, you'd see that every point on the surface moves away from every other point as the balloon expands. The farther apart two dots on the balloon's surface are, the faster they'll seem to move away from each other. Now, imagine living on the surface of a balloon that expands in 3 dimensions, not just 2. That's more like the universe. Every point in space is moving away from every other point as space itself stretches and grows. But here's where things get even stranger. While we can imagine this in 2D on the balloon's surface, in 3D, there's no outside for the universe to expand into. There's nothing beyond space. Space is everything. The universe isn't growing into an empty vacuum, because there's no empty outside of it. Space is creating itself as it expands. This is what scientists mean when they say space is expanding intrinsically. The fabric of space is stretching itself, not moving into some void. Let's take a moment to consider how this works on a cosmic scale. We're all familiar with the concept of gravity. It's the force that pulls everything toward each other. It's what keeps the Earth in orbit around the Sun, the Moon around Earth, and everything else locked in place. Gravity is powerful and affects everything, from the smallest particles to the largest galaxies. But when it comes to the vast distances between galaxies, gravity is not enough to stop the expansion of space. In fact, it's the expansion of space that's causing galaxies to move farther and farther away from each other. It's not the galaxies themselves moving through space. Rather, space is expanding, and the galaxies are simply being carried along for the ride. We feel gravity pulling us toward the Earth. But when you zoom out to the scale of galaxies and clusters of galaxies, the expansion of space dominates. And when you look at the vast distances between galaxies, the force of space's expansion far outweighs the pull of gravity. This means that, as the universe ages, galaxies that were once neighbors are now rushing away from each other at incredible speeds. This is why when we look out at the night sky, we see galaxies racing away from us. The farther a galaxy is from us, the faster it appears to be moving away. This realization was groundbreaking when it was first discovered by astronomer Edwin Hubble in 1929. Prior to that, scientists assumed the universe was static, unchanging, and fixed. But when Hubble looked at distant galaxies, he noticed something extraordinary. The light from these galaxies was redshifted, meaning the wavelengths of the light were stretched toward the red end of the spectrum. The farther away a galaxy was, the more its light shifted. This redshift wasn't because the galaxies were moving through space like cars on a highway. Instead, it was because space itself was expanding, stretching the light waves as they traveled. Hubble's discovery shattered the scientific understanding of the universe. The redshift was a clear sign that the universe was not static. It was dynamic, expanding and at an accelerating rate. Hubble's law, which states that the recession velocity of a galaxy is proportional to its distance from us, further cemented this idea. In simpler terms, the farther away a galaxy is, the faster it is moving away from us. This observation led to the now widely accepted idea that the universe began as a singular point, a tiny, infinitely dense spot that exploded in the Big Bang and has been expanding ever since. But here's the real kicker. When you think about the universe expanding, it's easy to imagine everything flying outward from some central point, like debris from an explosion. However, the expansion of the universe isn't centered on any one place. Every point in the universe is expanding, and every galaxy appears to be moving away from every other galaxy. No galaxy is at the center of the universe. It just feels that way from our perspective. If you were to travel to another galaxy and look out, it would appear that all other galaxies are moving away from you too. There's no center of the universe. This means that space is expanding everywhere, and every galaxy is the center of its own expanding space. The universe is expanding uniformly, and from any vantage point it looks like everything is racing away from you. But this expanding space is more than just a cosmic curiosity. It has profound consequences for our understanding of time, space, and the future of the universe. One of the most profound implications is that the universe as we know it has a finite age. The Big Bang occurred roughly 13.8 billion years ago, and since that time space has been expanding, carrying galaxies further apart. That means if we look far enough back in time, using the light from distant galaxies as a kind of cosmic time machine, we can trace the history of the universe back to that singular moment of creation. But the universe doesn't just expand at a constant rate. Over time, it has accelerated. For most of its history, gravity was the dominant force holding things together. But about 5 billion years ago, something strange started to happen. The rate of expansion began to increase. Scientists don't fully understand what caused this acceleration, but they have a name for it: dark energy. This mysterious force makes up about 70% of the universe, and is thought to be responsible for driving the accelerated expansion we see today. Dark energy is invisible, undetectable, and its effects are still one of the greatest mysteries in cosmology. We don't fully understand what dark energy is, but we do know that it's causing the universe to stretch faster and faster. The more space stretches, the more galaxies race away from each other. In some cases, galaxies are moving so fast that they exceed the speed of light. This might sound like a violation of physics, but it's not. The speed of light is only a limit on how fast objects can move through space, not how fast space itself can expand. As space expands, it can carry galaxies farther apart, and that's why we see distant galaxies moving faster than the speed of light. Now you might be thinking, if the universe is expanding, then what's it expanding into? And the answer is, it's not expanding into anything. Space itself is simply growing. It's a tough concept to wrap your head around, but it's one of the most important ideas in modern cosmology, and while this idea may seem strange, it helps us understand the behavior of the universe on the largest scales. Space doesn't need a container to grow into. It just grows, carrying everything within it along for the ride. This is what makes the universe's expansion so unique and so different from the way we understand objects and forces in our everyday world. The expansion of space is a key player in the larger story of the universe's fate. As space continues to stretch, the distances between galaxies will only grow. In the far future, galaxies will drift farther apart, and eventually, galaxies beyond our local group may be too far to see or communicate with. The fabric of the universe will continue to stretch, leading to a colder, emptier cosmos. This is where we get the idea of the Big Freeze or the heat death of the universe, a time when the universe has expanded so much that it reaches a state of maximum entropy, where no stars are left to shine, and everything is spread thin across an unimaginable vastness. So space is stretching. Galaxies are moving away from us. And as we look deeper into the universe, we're also looking back in time, tracing the history of the cosmos from the Big Bang to the present day. The idea that space itself is expanding isn't just a neat trick of the universe, it's the key to understanding everything from the birth of the universe to its eventual death. And while we don't have all the answers yet, every discovery we make about the expansion of space brings us one step closer to understanding the very nature of reality itself. Imagine for a moment you're standing in front of a giant telescope, gazing out at the vast expanse of the universe. You've just trained your eyes on the distant stars and galaxies, and what you see shakes you to your very core. Instead of the calm, steady universe that was once thought to exist, you observe a chaotic, rapidly expanding cosmos, where galaxies are fleeing away from each other faster than the speed of light. This is the universe as we now know it, a place where the laws of physics bend in ways that challenge everything we thought we understood. It was in the late 1920s when astronomer Edwin Hubble made a discovery that would completely alter our understanding of the universe. While peering through the world's largest telescopes at distant galaxies, Hubble saw something mind-boggling. The light from every galaxy appeared redder the farther away it was. This redshift wasn't just some random anomaly. It was a sign that these galaxies were moving away from us. In fact, the farther a galaxy was, the faster it seemed to be receding. This phenomenon suggested that not only were galaxies moving apart, but that the entire universe was expanding. Hubble's discovery didn't just change the way we thought about the universe. It completely dismantled the long-standing belief that the cosmos was static and unchanging. For centuries, scientists believed that the universe had existed in a fixed state. The idea of a static universe fit neatly with the prevailing notions of gravity and celestial mechanics. But Hubble's observations opened the floodgates to an entirely new way of understanding the cosmos. The universe is not static, it is dynamic, ever-changing, and constantly expanding. At the heart of this discovery was a simple yet profoundly unsettling observation. Galaxies far from us are moving away at speeds proportional to their distance. This observation, which came to be known as Hubble's law, suggested that the further a galaxy is from Earth, the faster it is receding. This was a radical shift in thinking. For centuries, humanity had believed itself to be at the center of the universe. But Hubble's law revealed something entirely different. No matter where you are in the universe, it will appear as if everything else is moving away from you. This is because the universe is expanding uniformly, and every point within it seems to be at the center of expansion. In a very real sense, Hubble had shown that there is no special center to the universe. Now this raises an obvious question. If the universe is expanding, where is it expanding into? The answer, as we've already hinted, is deeply strange. The universe is not expanding into anything. There's no outside of the universe. The universe itself, space itself, is stretching. Imagine a loaf of raisin bread in the oven. As the dough rises, the raisins inside move farther apart. They don't move through the dough, rather the dough itself expands, carrying the raisins along with it. In the same way, galaxies are not flying through space. Space itself is expanding, and it's carrying galaxies with it. This is a crucial point. The idea that galaxies themselves aren't moving through space is mind-bending. Rather, the space between them is stretching, and that's what causes them to appear as though they're speeding away from each other. If space is expanding, then the fabric of reality itself is changing. And this, in turn, changes how we think about everything from the structure of the universe to the laws of physics themselves. Hubble's discovery had far-reaching implications for our understanding of the universe's past. If galaxies are moving away from each other, then, logically, at some point in the distant past, they must have been much closer together. This led to the formulation of the Big Bang theory, the idea that the universe began as an incredibly dense hot point and has been expanding ever since. The evidence from Hubble's law suggested that everything in the universe was once compressed into a singularity, a single point of infinite density. This point of origin is what we call the Big Bang. But the Big Bang theory is often misunderstood. Many people imagine the Big Bang as some kind of giant explosion like a bomb going off. However, this analogy is misleading. The Big Bang wasn't an explosion in space. It was an expansion of space itself. Think about it like this. The universe didn't explode outward from a single point. Instead, space itself began to stretch, and as it did, it carried all matter and energy along with it. So in a sense, everything in the universe is still being carried along by this stretching fabric of space, continuing to expand, even as time moves forward. The evidence for this expansion, and the idea that the universe started from an extremely hot and dense state, is all around us. The most compelling evidence comes from the cosmic microwave background, CMB, a faint afterglow of radiation that fills the universe. This radiation is a snapshot of the universe when it was just 380,000 years old, and it provides a glimpse into the early stages of the universe's expansion. The CMB is one of the most powerful pieces of evidence supporting the Big Bang theory. It's like a baby picture of the universe, a cosmic fossil that shows us what the universe looked like in its infancy. But while the discovery of the expanding universe and the Big Bang theory were groundbreaking, they also raised even more questions. For one, if the universe is expanding, what does that mean for the future of the cosmos? Could this expansion continue indefinitely, or would it eventually slow down and collapse in on itself? For a long time, scientists believed that gravity would eventually slow down the expansion. After all, gravity is a force that pulls matter together. So if the universe was expanding, the force of gravity would eventually counteract that expansion, bringing everything back together. This idea led to the possibility of a big crunch, a scenario where the universe would eventually contract, collapsing all of matter back into a singularity. But this idea of a big crunch was put to the test in the late 1990s, when astronomers made a stunning discovery. They expected that the expansion of the universe would be slowing down, but instead they found that it was speeding up. This revelation came from observations of distant supernovae, exploding stars that act as standard candles for measuring distances in space. By studying the light from these supernovae, astronomers were able to measure the rate at which the universe was expanding, and what they found shocked them. The expansion was accelerating. This unexpected acceleration of the universe's expansion pointed to the existence of a mysterious force that was driving the cosmos apart. This force, which came to be known as dark energy, is thought to make up about 70%, but while we can observe its effects driving the accelerated expansion of the universe, we have no idea what dark energy actually is. Is it some kind of energy inherent in empty space? Or is it a property of the vacuum itself? Whatever it is, dark energy is one of the greatest mysteries in modern science. The discovery of dark energy had another profound implication. It meant that the universe's ultimate fate was now uncertain. If dark energy continues to accelerate the expansion of the universe, it could lead to what's known as the Big Freeze, a scenario where the universe continues to expand indefinitely, becoming colder and more dilute over time. Stars will burn out, galaxies will drift apart, and the universe will be left in a state of darkness and emptiness. But there's another possibility. Some theories suggest that dark energy might not remain constant. If it were to weaken or change over time, it could lead to a slowdown in the expansion of the universe, potentially even triggering a big crunch. In this scenario, the universe would collapse back in on itself, and everything would be drawn into a single point once again. The fact that we don't know whether dark energy will continue to accelerate the expansion of the universe or whether it will eventually slow down and reverse it is one of the most profound mysteries in cosmology. It's also what makes the study of the expanding universe so exciting. The universe's expansion is not just something that happened in the past, it's something that's still happening right now as we speak. And as we continue to study this expansion, we are bound to uncover even more incredible truths about the cosmos, its history and its ultimate fate. So, the universe is expanding, and it's expanding in ways that are more bizarre and more mind-blowing than we could have ever imagined. From Hubble's groundbreaking discovery to the modern mysteries of dark energy, the expansion of space is at the heart of some of the most exciting questions in science today. And as we continue to unravel the mysteries of cosmic expansion, we're left with more questions than answers. questions that might one day reveal the deepest secrets of the universe itself. The discovery of cosmic expansion in the 20th century brought with it a torrent of new questions and revelations, but one of the most mind-bending aspects of this cosmic puzzle revolves around the concept of redshift. When Edwin Hubble first made his monumental discovery that galaxies were moving away from each other, he observed that their light was stretched, moving toward the red end of the spectrum. This phenomenon, known as redshift, became one of the most significant pieces of evidence for the expanding universe. But redshift isn't just a curious scientific observation, it's a clue to a larger, more perplexing question. How do we understand the nature of the universe, especially when we see these distant galaxies moving at speeds that defy all common sense? At the heart of this mystery is the realization that when we observe the light from distant galaxies, we are not simply seeing their light as it was emitted. Instead, we are seeing light that has traveled across vast expanses of space, stretching and shifting as the universe itself expands. The redshift we observe is not just caused by the motion of the galaxies through space, but is a direct consequence of the stretching of space itself, a process known as cosmological redshift. It's the key to understanding the behavior of galaxies in an expanding universe, and it's also the cornerstone of much of what we know about the universe's history and future. Let's first break down the phenomenon itself. Light, as we know, is made up of electromagnetic waves that oscillate at specific frequencies. These frequencies determine the color of the light, with shorter wavelengths corresponding to the blue end of the spectrum and longer wavelengths corresponding to the red. When a galaxy is moving away from us, the light waves it emits are stretched, causing the wavelengths to become longer, shifting the light toward the red end of the spectrum. This stretching is what we observe as redshift. Now, here's where things get interesting. This redshift isn't like the Doppler effect we experience when a car zooms past us with its horn blaring. In the Doppler effect, the light waves are compressed as the object moves toward us and stretched as it moves away. This is what happens when an ambulance with its siren on approaches and then passes by. But cosmic redshift is different. It's caused by the stretching of space itself, not by the motion of objects through space. When galaxies move apart due to the expanding universe, the space between them stretches, and this stretching pulls the wavelengths of light along with it. The result: the further away a galaxy is, the more its light is redshifted, and the more we can infer about the distance and speed at which it is receding from us. It's crucial to understand that this redshift is not simply an optical illusion, it's an actual physical effect. And it's not just a small effect at the largest scales of the universe, it has profound consequences. When astronomers look at the most distant galaxies, they observe a shift in the light from those galaxies that is so extreme, the light is no longer visible to the human eye. Some of the most distant galaxies emit ultraviolet and visible light. But by the time their light reaches Earth, after traveling billions of years across expanding space, it is stretched into infrared wavelength. This phenomenon is not only a confirmation of the universe's expansion, but it also serves as a cosmic clock, giving us a glimpse into the universe's past. The relationship between redshift and distance is governed by one of the most fundamental observations of modern cosmology: Hubble's law. Hubble's law states that the farther away a galaxy is, the faster it appears to be receding from us. This relationship, in essence, is the observable signature of an expanding universe. It's what allows us to calculate the rate of expansion, something known as the Hubble constant. Here's the key takeaway: the redshift of light is directly related to the distance of the galaxy that emitted it. As space stretches, the light from these distant galaxies is stretched too. The more stretched the light, the farther away the galaxy must be. This cosmic stretching of light is one of the reasons why scientists are so confident that the universe is not static but expanding. Every galaxy, regardless of where it is moving away from every other galaxy, and this expansion is reflected in the redshift of their light. But the story doesn't end there. Redshift not only tells us about the distance and speed of galaxies, but it also holds clues about the universe's past and future. By studying the degree of redshift in distant galaxies, astronomers can map out the history of cosmic expansion. If we observe galaxies whose light has been redshifted by a significant amount, we are looking at galaxies that existed billions of years ago. The farther away a galaxy is, the further back in time we are looking. This provides astronomers with a powerful tool: the ability to trace the evolution of the universe from its earliest days all the way to the present. Now, this brings us to one of the most astonishing implications of redshift and Hubble's law: the Big Bang. If galaxies are moving away from each other, and the further away a galaxy is, the faster it recedes, then if we reverse this process, take the expansion back in time, all the galaxies would eventually converge at a single point. This is the essence of the Big Bang theory. The universe at some point in the past must have been condensed into an incredibly small, hot and dense state. The universe we see today was once packed into a singularity, a point of infinite density, and has been expanding ever since. The discovery of redshift gave astronomers a way to observe this expansion in real time. By measuring the amount of redshift in light from distant galaxies, scientists can trace the rate at which the universe is expanding and even estimate its age. The fact that we can see galaxies that are billions of light years away and measure their redshift is proof that light has been traveling through an expanding universe for billions of years. It's like looking into the past, and every galaxy we see tells a story about the universe at a particular moment in time. But while redshift has helped to confirm many of the basic principles of cosmology, it has also raised new questions. For one, if galaxies are moving away from us at such high speeds, how fast is the universe expanding, and what is the exact rate of this expansion? The answer to this question is encapsulated in the Hubble constant, a value that determines the rate of expansion of the universe. The Hubble constant is crucial because it allows us to calculate distances to galaxies based on their redshift, which in turn provides insight into the size, age, and ultimate fate of the universe. However, the Hubble constant itself is not a settled issue. Over the years, astronomers have used a variety of methods to measure this constant, but two different techniques have led to conflicting results. Some measurements, based on observations of the cosmic microwave background (CMB) radiation, suggest that the Hubble constant is around 67 kilometers per second per megaparsec. Other measurements, based on observing nearby galaxies, suggest it is closer to 73 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, has left cosmologists scratching their heads. What does it mean if the rate of expansion is different than we expected? Could it be that we are missing something fundamental in our understanding of the universe? This is where the redshift mystery takes another twist. If the expansion of the universe is accelerating, as we've discovered through the study of distant supernovae and the effects of dark energy, then the amount of redshift we observe should be consistent with the rate of expansion. But if two independent methods for measuring the expansion rate are giving different results, what does that tell us about our understanding of cosmological principles? Could there be new forces at play, forces that we've yet to understand, that are affecting the way galaxies recede from each other? Or is this simply an error in our measurements, one that we haven't yet resolved? While the exact answer to the Hubble tension remains unclear, the key takeaway from the redshift and Hubble's law is this: we are looking at a universe that is constantly changing, stretching, and expanding, and these changes have been happening for billions of years. Redshift is the cosmic fingerprint, the signature of this expansion. By studying the redshift of light from distant galaxies, astronomers are not just measuring the velocity of galaxies, they're measuring the history of the universe itself. This brings us to another important point: the future of the universe. As space continues to stretch, galaxies will move farther and farther apart. Eventually, distant galaxies will be so far away that their light will never reach us. In the far future, our observable universe will shrink to just our local group of galaxies, and everything else will be beyond our reach. In this scenario, the redshift of light will only continue to increase, and the universe will become colder, darker, and emptier. The redshift we observe today is just a preview of what's to come, a cosmic warning of the future of the universe. In the end, redshift is more than just a tool for measuring the speed of galaxies. It's a window into the universe's past, present, and future. It shows us how the cosmos has evolved over time, how it continues to evolve, and how it will ultimately reach its end. As we continue to study the redshift of distant galaxies, we're not just observing the movement of stars and galaxies, we're observing the very nature of space and time itself, and learning more about the incredible, ever-expanding universe in which we live. The Big Bang is one of the most famous yet often misunderstood concepts in cosmology. While the name may conjure images of an explosion, fireworks bursting from a single point in space, nothing could be further from the truth. The Big Bang wasn't an explosion in space. It was the expansion of space itself, an event that marked the birth of the universe as we know it. When we talk about the Big Bang, we are talking about the beginning of both space and time, a moment when the universe as a whole began to stretch, carrying with it all matter and energy in a rapid, unimaginable expansion. But what did the Big Bang really look like? And what happened in the moments before and after? The story begins with the fundamental understanding that the universe hasn't always been the vast, sprawling expanse we see today. In fact, it was once confined to a singularity, a point so small, so dense, that the laws of physics as we know them break down. Everything we know, every galaxy, every star, every planet, was contained in this infinitesimally small point. Then, in an event that defies common understanding, space itself began to stretch outward, expanding at an incredible rate. This initial phase of rapid expansion is called cosmic inflation, and it is one of the most important concepts in modern cosmology. During inflation, the universe expanded at an incomprehensible speed, far faster than the speed of light, and in less than a fraction of a second it grew from smaller than an atom to a size larger than a galaxy. Imagine a tiny speck, smaller than a proton, suddenly inflating to the size of a grapefruit. It's mind-boggling, but that's essentially what happened. The universe expanded by a factor larger than the number of atoms in the observable universe in less than the blink of an eye. It was an expansion so rapid that it still affects the universe today. This period of inflation explains several cosmic mysteries. One of the most profound is the homogeneity of the universe. The fact that when we look in any direction, the universe looks largely the same. There are no big differences in the properties of distant regions of space that could have had the time or ability to communicate with one another. This uniformity of the universe, how distant parts appear nearly identical, can only be explained by inflation. During this period, tiny regions of space were stretched across vast distances at unimaginable speeds, ensuring that the universe became remarkably homogeneous in its earliest moment. But after inflation ended, the universe didn't remain the same size. It continued expanding, though at a much slower rate. In fact, for much of the universe's early history, the expansion was far slower than it was during inflation, but it was still incredibly rapid in terms of the distances involved. Immediately after inflation, the universe was a hot, dense, and energetic place. The particles that make up everything in the universe, quarks, electrons, neutrinos, were all in a high-energy state, and they were interacting in ways we can't directly observe today. As the universe cooled, atoms began to form. The very first atoms were primarily hydrogen and helium, and these atoms formed during a period known as recombination. It was during this time that the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms. These atoms then allowed light to travel freely through space for the first time in cosmic history. Before this moment, the universe was opaque. Light was constantly scattered by free electrons, and nothing could travel very far. Once the first neutral atoms formed, the universe became transparent, and light could travel freely through space. This moment, about 380,000 years after the Big Bang, is incredibly significant because it marks the moment when the universe transitioned from being a foggy, dense soup of particles to the vast, mostly empty space that we see today. The light that was emitted at this moment, the cosmic microwave background radiation, is still present today, and it provides us with a snapshot of the universe in its infancy. In fact, this radiation is often referred to as the baby picture of the universe, and it holds crucial information about the conditions that existed when the universe was just a fraction of its current age. The cosmic microwave background (CMB) radiation is a faint glow that permeates the entire universe, and it carries with it valuable information about the early universe's temperature, density, and composition. By studying the CMB, scientists can gain insights into the universe's age, its rate of expansion, and the distribution of matter in its earliest moments. What's even more fascinating is that the CMB radiation we observe today was once a powerful source of light, but it has been stretched to longer wavelengths, shifting from visible light to microwave radiation due to the expansion of space over billions of years. While the CMB is a treasure trove of information about the early universe, the most exciting discoveries are still to come. In recent years, advanced technologies like the James Webb Space Telescope have allowed astronomers to peer further back in time than ever before. Webb's infrared observations of distant galaxies and stars are giving us new insights into the first galaxies to form in the universe, allowing us to understand how galaxies evolved from the early dense universe into the massive structures we see today. The early universe was a harsh, chaotic place, filled with high-energy radiation and an abundance of particles colliding and interacting. Over time, as the universe continued to expand and cool, it allowed for the formation of the first stars, galaxies, and the intricate structures we observe in the cosmos today. These first stars were much different from the stars we see today: hotter, more massive, and more unstable. They formed from clouds of gas and dust, and their intense radiation helped reionize the universe, clearing away the hydrogen gas that had once blocked light. As these first stars formed and began to shine, they sparked the process of cosmic reionization, a period when the universe was filled with light for the first time. Before reionization, the universe was a dark place, atoms were neutral, and light couldn't travel freely. After reionization, the universe was bathed in light from stars, and this marked the birth of the first galaxies. This gradual process of cooling, expanding and forming stars was the start of a long journey toward the universe we see today. The universe was still in its youth during these early stages, and it would take billions of years for galaxies to form clusters, stars to evolve into the complex objects they are today, and for planets like Earth to emerge. But even as stars and galaxies formed, the basic shape and structure of the universe was being set. Space itself continued to stretch and expand, pulling galaxies farther apart. And this expansion hasn't slowed down. In fact, it continues at an accelerated rate today, driven by the mysterious force known as dark energy. Dark energy, a force that makes up about 68% of the universe, is believed to be responsible for the accelerated expansion of the universe that we observe today. The nature of dark energy is still one of the biggest mysteries in cosmology. We can see its effects. Galaxies are moving away from each other faster and faster, but we don't fully understand what it is. Some theories propose that dark energy is a property of space itself, while others suggest it may be related to quantum mechanics or even extra dimensions. Despite the mysteries of dark energy, one thing is clear: the universe is still expanding, and it's expanding faster than ever. This expansion, which started with the Big Bang and continued through cosmic inflation, is a key part of the story of the universe's evolution. It has shaped the very structure of the cosmos, and will continue to do so for billions of years to come. But what does this mean for the ultimate fate of the universe? If the expansion continues at an accelerating rate, then eventually the universe will become a cold, dark, and empty place. Stars will burn out, galaxies will drift apart, and the universe will be left in a state of maximum entropy, where everything is spread so thin that no new events can occur. This scenario, known as the Big Freeze, represents one possible end to the universe. In the far future, as dark energy continues to drive the expansion, the universe could be left in a state of complete isolation. Isolated galaxies, isolated stars, and eventually isolated particles, drifting through an infinite empty space. Alternatively, if dark energy were to change or decrease in strength, the expansion could slow down, and the universe might eventually collapse in on itself in a big crunch. In this scenario, galaxies, stars, and all matter would be pulled back together by gravity, eventually collapsing into a singularity. The idea of a big crunch raises intriguing questions about the nature of time and space. Could the universe be caught in an endless cycle of expansion and contraction? For now, the fate of the universe remains unknown. Whether it will continue to expand forever, slowly winding down into cold emptiness, or eventually collapse back on itself in a big crunch, the answer lies in understanding dark energy and how it will shape the future of the cosmos. But no matter what happens, the Big Bang remains the key event that set the entire process into motion. The birth of everything, from the first moments of cosmic inflation to the far future that we can only imagine today. The Big Bang theory is not just about understanding where the universe came from, it's about understanding how the universe works. It's about tracing the path from the beginning of space and time to the vast, expanding cosmos we observe today. It's the story of how everything, matter, energy, space, and time came to be, and how the universe continues to evolve, from the intense heat of the early universe to the formation of stars and galaxies, and onto the mysteries of dark energy. The Big Bang is not just a historical event, it is the ongoing process that defines the very nature of existence. As we continue to unravel the mysteries of the universe, one of the most perplexing and counterintuitive elements we encounter is the nature of the speed of light and the implications it has on our understanding of cosmic expansion. According to Einstein's theory of relativity, nothing can travel faster than the speed of light. Nothing with mass, at least. The speed of light is often treated as an absolute limit, a universal speed that no object, no matter how powerful, can support. But as we delve deeper into the behavior of galaxies and the expansion of space itself, we encounter situations where galaxies appear to move faster than light, challenging our understanding of the fundamental limits of the universe. This apparent violation of the speed limit is not as paradoxical as it seems once we distinguish between two types of motion. In general relativity, the speed of light applies to objects moving through space, not to the expansion of space itself. This distinction is crucial for understanding why galaxies can appear to move away from each other at superluminal speeds, faster than light, without violating the laws of physics. The key lies in understanding how space itself is expanding and carrying galaxies along for the ride. Imagine space as a fabric, stretching out in every direction. As the universe expands, this fabric of space stretches, and everything within it, galaxies, stars, and even light, are carried along by that expansion. The galaxies themselves aren't traveling through space like objects speeding down a highway. Instead, the space between galaxies is increasing, and the galaxies are simply moving apart because the space between them is stretching. This is analogous to the way points on the surface of a balloon move farther apart as the balloon inflates. The points aren't moving through the surface itself is expanding, pushing the points farther away from each other. In this framework, it's not a violation of the laws of physics for galaxies to move apart at speeds faster than light. Since the galaxies aren't actually moving through space at superluminal speeds, there's no need to apply the speed limit of light to them. Instead, the space between them is expanding, and as this expansion accelerates, it can carry galaxies away from each other faster than light would travel through the space in between. In fact, this phenomenon is not only possible but expected in an expanding universe. The farther apart two galaxies are, the faster the space between them will expand, and the faster they will appear to recede from each other. This effect is particularly evident in the most distant galaxies. When we observe galaxies billions of light-years away, their light has traveled across vast stretches of expanding space. As the universe has expanded, the wavelengths of the light from these distant galaxies have been stretched, shifting the light toward the red end of the spectrum. This stretching of light, called cosmological redshift, is a direct result of the expansion of space. The greater the distance between us and a galaxy, the more its light is stretched, and the faster it appears to be receding from us. It's important to note that this isn't some form of optical illusion or a trick of perception. The galaxies aren't just appearing to move faster than light, they actually are. The light that reaches us from distant galaxies is redshifted because the space it has traveled through has expanded during its journey. In this sense, the galaxies are moving away from us at faster than light speeds, but the light they emit is still bound by the speed of light in terms of its travel through space. It's the space itself that is expanding faster than light, not the galaxies or their light. This revelation has profound implications for our understanding of the universe. If galaxies can move apart faster than light, what does that mean for the ultimate fate of the cosmos? We've known for some time that the universe is expanding, but what happens when that expansion accelerates? As the space between galaxies continues to stretch, the distances between them will continue to grow, and eventually, some galaxies will reach a point where their light can no longer reach us. This is the concept of the cosmic horizon, a boundary beyond which galaxies recede faster than light, making it impossible for their light to ever reach us. This phenomenon has already begun to take place. The most distant galaxies we can observe are already receding so quickly that their light has been stretched beyond the visible spectrum, leaving us with only faint traces of their existence. As the universe continues to expand, more and more galaxies will cross this threshold and disappear from our observable universe. This represents a kind of cosmic censorship, where entire regions of space will become fundamentally unobservable, no matter how advanced our technology becomes. The light from these galaxies will never reach us, and we will be left in an ever darker, emptier universe. But this isn't the only way in which the expansion of space leads to faster-than-light phenomena. Another key element to understand is that the rate of expansion itself isn't constant. It has changed dramatically over the history of the universe. For the first few billion years after the Big Bang, the expansion of the universe was slowing down, as gravity exerted its influence and pulled matter together. However, about 5 billion years ago, something remarkable happened. The expansion of the universe began to accelerate, and the force driving this acceleration is what we now call dark energy. Dark energy is a mysterious force that makes up about 68% of the universe's total energy content. Its effect on the expansion of the universe is profound. It not only counteracts the pull of gravity, but actually causes the expansion of space to speed up over time. While the exact nature of dark energy remains one of the greatest unsolved mysteries in modern physics, We know that it is responsible for the accelerating expansion of the universe. As dark energy continues to dominate the cosmic landscape, galaxies will continue to move away from each other faster and faster, pushing the boundaries of the observable universe even further out of reach. This accelerating expansion means that, in the future, distant galaxies will be moving away from us at speeds that exceed the speed of light, and their light will never be able to reach us. The universe, as seen from our perspective, will become increasingly isolated. This will lead to a phenomenon known as the Big Freeze, where galaxies, stars, and all other cosmic structures are pulled apart by the relentless expansion of space. As stars burn out and galaxies drift away, the universe will become colder, darker, and emptier, eventually reaching a state where nothing of interest will ever happen again. The ultimate fate of the universe, under the influence of dark energy, is one of endless expansion and isolation. However, there is another possibility, albeit one that is less likely given our current understanding. If dark energy were to weaken or change in some way, the expansion of the universe could slow down. In this scenario, the gravitational pull of matter could eventually overcome the expansion, causing the universe to collapse in on itself in a catastrophic event known as the Big Crunch. In this scenario, galaxies would be drawn back together, stars would burn out and collapse, and the universe would ultimately collapse back into a singularity, marking the end of everything. The idea of a Big Crunch presents a fascinating paradox. If the universe collapses in on itself, could this lead to a new Big Bang, restarting the cycle of expansion and contraction? Some theories suggest that the universe could be caught in an infinite loop of Big Bangs and Big Crunches, cycling through periods of expansion and contraction forever. However, this idea remains speculative, and our best evidence suggests that the universe will continue to expand indefinitely, ultimately leading to the Big Freeze. Even more intriguing, some theories suggest that the expansion of the universe might not be the only force at play. As the universe continues to stretch and galaxies move farther apart, new dimensions, parallel realities, or hidden forces could influence the outcome of cosmic expansion. These ideas, though speculative, highlight the importance of understanding the true nature of dark energy and the forces that drive cosmic acceleration. Could we be on the brink of discovering new laws of physics that will radically change our understanding of the universe? In the end, the expansion of space and the faster-than-light recession of galaxies force us to reconsider our fundamental ideas about space, time, and the limits of the cosmos. The universe is not just a static backdrop for the events that unfold within it. It is a dynamic, ever-changing entity that is stretching and growing, carrying galaxies and stars along for the ride. The speed of light is not an absolute limit on the universe's expansion. It's simply a rule that applies to objects moving through space, not to space itself. As space continues to stretch, galaxies will race away from us faster than light, but that doesn't mean they're breaking the laws of physics. Instead, it's a sign that the universe is more mysterious, more strange, and more awe-inspiring than we could have ever imagined. The concept of the cosmic horizon is one of the most profound and unsettling aspects of modern cosmology. It forces us to rethink not only our place in the universe, but also the very nature of reality itself. As the universe continues to expand at an accelerating rate, there is a boundary beyond which galaxies will recede faster than the speed of light. This boundary is known as the cosmic horizon. Once a galaxy crosses this horizon, it will be permanently beyond our reach. Its light will never be able to reach us again. We will be left unable to observe or communicate with these distant regions of the universe, effectively rendering them invisible to us forever. The idea of a cosmic horizon arises naturally from the expansion of space. As we've already discussed, space itself is stretching, and this stretching causes galaxies to move away from each other. This expansion is not limited to just a few nearby galaxies. It affects the entire universe. The farther away a galaxy is from us, the faster it appears to be receding, and the greater the stretching of space between us and that galaxy. This means that over time, more and more galaxies will be moving away from us at speeds faster than light, and their light will become increasingly redshifted, eventually stretching so much that it shifts beyond the visible spectrum. The cosmic horizon represents the maximum distance from which light can travel to us in the age of the universe. Light from any galaxy beyond this horizon will never reach Earth, because the space between us is expanding too quickly for the light to keep up. Imagine, if you will, that the universe is like a balloon being inflated. As the balloon expands, the dots on its surface move farther apart. Now imagine that, Instead of the surface of a balloon, we're dealing with the fabric of space itself. As the universe expands, galaxies move farther apart, and eventually they reach a point where their light can no longer travel to us. This cosmic horizon is constantly shifting as the universe ages. As the expansion of the universe accelerates, the horizon grows farther away, and the regions of the universe that were once visible to us are slowly pulled beyond the reach of light. This process is gradual, but it's inevitable. In a few billion years, many galaxies that we see today will be too far away for us to observe or communicate with. Even galaxies that are currently part of our local group, such as the Andromeda Galaxy, will eventually be separated from us by vast stretches of space, and their light will no longer be able to reach us. This is a particularly disturbing realization for astronomers who rely on the observation of distant galaxies to study the history and evolution of the universe. As galaxies slip beyond the cosmic horizon, they will become unreachable. This means that there is a limit to how much we can know about the universe's past and future. Even if we develop advanced technologies that allow us to peer deeper into space than ever before, we will still be unable to observe the parts of the universe that have crossed the cosmic horizon. In a sense, the universe will become increasingly fragmented, with parts of it disappearing from view as they recede beyond the reach of light. This idea also poses some fundamental questions about the ultimate fate of the universe. If galaxies continue to move away from each other at accelerating speeds, and if the expansion continues indefinitely, then the universe will eventually become a place where the vast majority of galaxies are permanently unreachable. The observable universe will shrink to just a tiny fraction of the vast cosmic expanse. This is one of the consequences of the Big Freeze scenario, where the universe keeps expanding until it reaches a state of maximum entropy, where everything is spread so thin that no new events can occur. As galaxies recede beyond the cosmic horizon, the observable universe will become more and more isolated. This isolation will eventually become complete. The galaxies that remain within our cosmic horizon will become increasingly isolated from each other. Eventually, the last remaining galaxies within our observable universe will be left alone, as all the others have moved beyond our reach. These remaining galaxies will continue to expand away from each other, and as time goes on, stars will burn out, leaving behind cold, lifeless remnants. The universe will grow darker and colder, and there will be no way to reach out to other parts of the universe or communicate with the civilizations that might have once existed in distant galaxies. This concept of isolation goes beyond the mere physical separation of galaxies. It also suggests that the universe in its distant future will be a place where no new information can be exchanged. As the distances between galaxies grow ever larger, and as light from distant regions becomes forever unreachable, the universe will be a place where nothing can happen. The lack of interaction between distant regions of the universe means that the cosmos will become a static, unchanging place. The potential for new discoveries, for further evolution, or for the creation of new stars and galaxies will be stifled, as the universe enters a state of irreversible entropy. This cosmic isolation also raises questions about the ultimate meaning of existence. If the universe continues to expand indefinitely, and if regions of it become permanently invisible and unreachable, then it seems that the universe is destined to become a place of profound loneliness. The idea that entire galaxies will slip beyond the cosmic horizon and be forever lost to observation is a stark reminder of the vastness and inaccessibility of the cosmos. It challenges our human sense of scale and purpose, forcing us to confront the possibility that the universe may eventually become a place where nothing of significance ever occurs. At the same time, this realization adds a new layer of urgency to our exploration of the cosmos. If the universe is indeed expanding toward a state of isolation and entropy, then understanding the cosmic horizon and the limits of observation becomes more important than ever. We need to learn as much as we can about the universe while we still have the opportunity to observe it. The more we discover about the universe, the more we come to appreciate the fragile nature of our ability to observe and understand it. The cosmic horizon reminds us that our time to study the universe is finite, and that our knowledge will always be limited by the rate of expansion and the ever-increasing distance between us and the farthest reaches of the cosmos. In addition to this philosophical dimension, the concept of the cosmic horizon also has practical implications for the future of space exploration. As space exploration technologies continue to advance, we might eventually reach a point where we are able to travel vast distances and explore galaxies that were once beyond our reach. However, as galaxies move farther away, their light will become increasingly redshifted, and even our most advanced spacecraft will eventually reach a point where they can no longer travel fast enough to catch up with the galaxies that are moving beyond the cosmic horizon. In the far future, human exploration of the cosmos will become increasingly constrained by the limits of the cosmic horizon. Despite these challenges, the concept of the cosmic horizon highlights the incredible potential of our understanding of the universe. The fact that we can observe galaxies billions of light years away and study the expansion of the universe is a testament to the power of human ingenuity and curiosity. Even though the universe is expanding and galaxies are moving farther away, we are still able to explore and understand the vast cosmos in ways that were once thought impossible. Ultimately, the cosmic horizon reminds us of the transience of our place in the universe. As galaxies move away and become unreachable, and as the observable universe shrinks to a fraction of its current size, we are left with a powerful, humbling realization: the universe is not a static entity, but a dynamic, ever-changing system. The cosmic horizon forces us to confront the limits of our knowledge and our existence, and it challenges us to explore and understand the universe while we still have the opportunity. As the universe expands and the galaxies recede, we are reminded of how fleeting our ability to observe and engage with the cosmos truly is. In this sense, the cosmic horizon is both a limit to our understanding and a call to action, a reminder that the universe is vast and our time to study it is precious. In the quest to understand the universe, one of the most captivating and mysterious forces that continues to elude scientists is dark matter. While we can observe its effects in the cosmos, we still know very little about its true nature. Dark matter doesn't emit light, nor does it interact with electromagnetic forces the way ordinary matter does. Instead, it only reveals its presence through its gravitational influence, making it one of the most elusive components of the universe. But despite the fact that we can't see it or touch it, dark matter is essential to our understanding of the universe, and it plays a pivotal role in the formation of galaxies, galaxy clusters, and the very structure of the cosmos. The first hints that something unseen was influencing the movement of galaxies came in the early 20th century. Astronomer Fritz Zwicky, while studying the Coma Galaxy cluster in 1933, noticed that the galaxies within the cluster were moving much faster than they should have been, given the amount of visible matter present. He proposed that there must be some unseen matter in the cluster, a form of matter that didn't emit light or energy, but whose gravitational pull was influencing the motion of the galaxies. Zwicky's theory, which he called dark matter, was met with skepticism at the time, but over the decades, further observations began to confirm his suspicions. One of the most compelling pieces of evidence for dark matter came in the 1970s, when astronomer Vera Rubin studied the rotation curves of galaxies. When you observe a galaxy from the outside, you expect that the stars at the outer edges of the galaxy would be moving slower than those near the center due to the gravitational pull of the galaxy's visible matter, like stars and gas. However, Rubin's observations showed something strange. The stars at the outer edges of galaxies were moving just as fast as those closer to the center. This was an anomaly. According to the laws of physics, there shouldn't have been enough visible matter to account for this speed. Rubin's findings pointed to the existence of something else, something invisible, that was exerting additional gravitational pull and influencing the motion of stars in galaxies. This unseen mass became known as dark matter. Over time, more and more evidence accumulated, and scientists came to realize that dark matter is a fundamental part of the universe, making up about 27% of the total mass-energy content of the cosmos, far more than the ordinary matter we see and interact with, which only accounts for about. Yet despite this overwhelming evidence for dark matter's existence, we still don't know what it is made of. There are many theories, but no definitive answers. One of the leading candidates for dark matter is a class of hypothetical particles known as WIMPs, weakly interacting massive particles. These particles would have mass, which would explain the gravitational effects we see, but they would interact only through gravity and the weak nuclear force, making them nearly impossible to detect using traditional methods. WIMPs are a popular theory because they would be consistent with the observed behavior of galaxies and clusters of galaxies. Another potential candidate is axions, which are extremely light, weakly interacting particles that could also account for the gravitational effects attributed to dark matter. Axions have been proposed as a solution to the strong CP problem in particle physics, but they could also play a role in the dark matter puzzle. While axions haven't been detected yet, they remain an active area of research, and experiments continue to search for their elusive signature. There's also a more radical hypothesis known as modified gravity, which suggests that the observed effects of dark matter might not be due to some mysterious substance, but instead could be explained by altering our understanding of gravity itself. One popular theory in this vein is MOND, modified Newtonian dynamics, which proposes that the laws of gravity behave differently at very large distances or in low acceleration environments. While MOND can explain some of the observations associated with dark matter, it struggles to account for all of them, particularly the way dark matter behaves in galaxy clusters. Despite these competing theories, the existence of dark matter remains one of the most pressing questions in modern physics. Its gravitational effects are observed on cosmic scales, and without it, many of the structures we see in the universe, like galaxies, galaxy clusters, and the vast cosmic web, would simply not be able to form. Dark matter acts like a cosmic scaffolding, providing the gravitational pull needed for galaxies to hold together. Without dark matter, the universe would look very different. Galaxies would fly apart, stars wouldn't be able to form as efficiently, and the structure of the cosmos would be far less organized. One of the biggest challenges in studying dark matter is that, unlike ordinary matter, it doesn't emit, absorb, or reflect light. This means that we can't observe it directly using telescopes or other traditional tools. Instead, we have to rely on its gravitational influence to detect it. This is similar to how astronomers first discovered the existence of black holes. By observing the way objects around them move, scientists inferred that something invisible and incredibly dense must be exerting a powerful gravitational pull. A prime example of this indirect detection comes from the study of galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies. When scientists study the motion of galaxies within these clusters, they find that the visible matter, such as stars and gas, isn't enough to account for the galaxy's speeds. The additional gravitational pull required to explain these speeds must come from dark matter, which makes up the bulk of the mass in galaxy clusters. One of the most striking pieces of evidence for dark matter comes from gravitational lensing. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, the gravitational pull of the object bends the light, creating a distorted image of the background galaxy. This effect, known as gravitational lensing, has been used to map the distribution of dark matter in galaxy clusters. By observing the way light is bent, scientists can infer the presence and distribution of dark matter even though it doesn't emit light. Gravitational lensing has provided one of the most direct ways to detect dark matter and understand its role in the formation of large-scale cosmic structures. While dark matter doesn't interact with light or ordinary matter in the same way that we're accustomed to, it does interact with gravity in a profound way. It's this gravitational influence that allows scientists to study dark matter and piece together its properties. The fact that dark matter is so pervasive and yet so invisible to us is a testament to the strange and mysterious nature of the cosmos. It's a reminder that our universe is full of phenomena that challenge our understanding of reality, pushing the limits of what we thought was possible. But what if dark matter isn't just a key to understanding the structure of the universe? What if it holds the answers to even bigger questions? Could dark matter play a role in the very formation of life, or in the fundamental workings of the cosmos? Some theories suggest that dark matter could be related to the formation of the first stars and galaxies. In the early universe, dark matter may have acted as a catalyst, pulling together gas clouds and allowing them to collapse and form the first galaxies. In this sense, dark matter may have been essential in kickstarting the process of cosmic evolution. Dark matter may also hold the key to understanding some of the most fundamental mysteries of physics. It may be connected to the elusive concept of dark energy, a mysterious force that's driving the accelerated expansion of the universe. While dark matter pulls things together through gravity, dark energy seems to be pushing things apart, accelerating the expansion of the universe. The relationship between these two forces, dark matter and dark energy, could provide a deeper understanding of the fate of the universe, the nature of space and time, and the very fabric of reality itself. Despite the enormous advances in our understanding of dark matter over the past few decades, we are still far from understanding its true nature. Every new piece of evidence, every experiment and observation brings us closer to unraveling the mystery. But in many ways, dark matter remains an enigma, a force that governs the cosmos but remains invisible to us. The search for dark matter, whether through the detection of WIMPs, axions, or the study of gravitational lensing, continues to be one of the most exciting and crucial endeavors in modern science. And as we move forward in our understanding, one thing is clear: dark matter is not just a footnote in the story of the universe, It's a central player in the drama of cosmic evolution, a mysterious force that shapes the very structure of everything we know. The study of dark energy has become one of the most intriguing and perplexing chapters in the story of the universe's expansion. For decades, we thought we had a solid understanding of the forces shaping the cosmos: gravity, the expansion of space, and the matter that fills it. Yet in the late 1990s, astronomers discovered something astonishing. The universe is expanding faster than it ever has before, and there's an invisible force driving that acceleration. This mysterious force, which we now call dark energy, is responsible for the observed acceleration in the expansion of the universe. But despite being one of the most significant discoveries in modern cosmology, dark energy remains one of the greatest mysteries in science. At first glance, dark energy might seem like an abstract concept, just another force in the universe that we can't see, touch, or directly measure. But in reality, dark energy is anything but abstract. It is the dominant force shaping the large-scale structure of the universe and determining its ultimate fate. Understanding dark energy is crucial if we want to comprehend the future of the cosmos, the nature of space and time, and the evolution of the universe from its birth in the Big Bang to its distant end. The story of dark energy begins with an observation that defied the expectations of astronomers. In the 1990s, a team of astronomers, led by Saul Perlmutter, Adam Rees, and Brian Schmidt, was studying distant supernovae, exploding stars that serve as standard candles for measuring distances in the universe. They expected that the expansion of the universe, which had been slowing down due to gravity, would continue at a decelerating pace as galaxies and other cosmic objects were drawn toward each other. However, to their shock, the supernovae they observed were farther away than they should have been, based on the expected slowing of the expansion. The universe wasn't slowing down, it was speeding up. This discovery was revolutionary. The realization that the expansion of the universe was accelerating meant that some force, unknown to science at the time, was driving the cosmos apart. That force, as it turned out, was dark energy. But this was just the beginning of the puzzle. While we now know that dark energy is responsible for this acceleration, understanding what it actually is remains one of the greatest challenges in modern physics. To put this into perspective, dark energy makes up about 68% of the universe's total energy content. The remaining 32% is divided between ordinary matter, about 5%, and dark matter, about 20%. This means that the vast majority of the universe is made up of something we can't see, touch, or directly measure. Dark energy is more than just a minor player in the cosmic game. It is the dominant force governing the expansion of the universe. Dark energy's discovery forces us to rethink everything we know about space and time. According to Einstein's theory of general relativity, gravity is the force that attracts objects toward each other. But dark energy behaves in the opposite way. Instead of pulling matter together, it pushes it apart. In fact, it's causing space itself to stretch at an accelerating rate, pushing galaxies farther and farther apart. This means that, over time, the distances between galaxies will continue to grow, making the universe even more vast and disconnected. One way to think about dark energy is in terms of the cosmological constant, a concept introduced by Albert Einstein in 1917. The cosmological constant was originally proposed by Einstein as a fudge factor to maintain a static, unchanging universe. At the time, scientists believed the universe was stable and eternal, but Einstein's equations predicted that gravity would eventually cause the universe to collapse. To counter this, he introduced the cosmological constant, which acted as a repulsive force to balance gravity and keep the universe from collapsing. After Edwin Hubble discovered that the universe was expanding, Einstein abandoned the idea of the cosmological constant, calling it his biggest blunder. However, in light of the recent discovery that the expansion of the universe is accelerating, the cosmological constant has made a comeback. Now it is thought to the effects of dark energy, an energy that permeates all of space and drives the accelerated expansion of the universe. The cosmological constant, in this sense, is a mathematical representation of dark energy's influence on the fabric of space-time. But the cosmological constant is not the only theory that could explain dark energy. Some scientists propose that dark energy is not constant, but instead varies across space and time. This idea is known as quintessence, and it suggests that dark energy might be a dynamic field that evolves over time. Unlike the cosmological constant, which is fixed, quintessence would allow dark energy to change in strength and behavior as the universe evolves. Quintessence remains a theoretical concept for now, but it provides a possible explanation for the accelerating expansion of the universe, one that doesn't rely on the assumption of a constant energy. Despite the fact that dark energy accounts for the vast majority of the universe's energy content, we know surprisingly little about it. The fact that dark energy is so pervasive yet invisible makes it incredibly difficult to study. It doesn't interact with light or matter in the way ordinary energy does, so it doesn't leave any detectable signature that we can observe directly. This is why scientists have had to rely on indirect methods, such as the study of distant supernovae, the cosmic microwave background radiation, and the large-scale structure of the universe, to understand its effect. One of the key pieces of evidence for dark energy comes from the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang. By studying the CMB, scientists can gain insights into the early conditions of the universe and how it has evolved over time. The CMB provides us with a snapshot of the universe when it was just 380,000 years old, and it reveals the amount of matter, energy, and curvature in the universe. The CMB also provides clues about the nature of dark energy, as it reflects how the expansion of the universe has changed over time. Another important piece of evidence for dark energy comes from the large-scale structure of the universe. Galaxies are not evenly distributed throughout space. Instead, they form a vast, interconnected web-like structure with clusters of galaxies and voids in between. The distribution of galaxies and the way they move can provide clues about the influence of dark energy on the universe's expansion. Observations of the large-scale structure of the universe suggest that dark energy is playing a key role in shaping the way galaxies are distributed and how they evolve. One of the most pressing questions about dark energy is whether it will continue to accelerate the expansion of the universe indefinitely, or whether it will eventually slow down. If dark energy remains constant, the universe will continue to expand at an accelerating rate, and galaxies will eventually be so far apart that they will be unreachable, even by the fastest spacecraft. This scenario, known as the Big Freeze, would result in a cold, dark and empty universe where no new stars or galaxies could form. All that would remain are isolated remnants of stars and black holes, drifting through an ever-expanding void. However, if dark energy is not constant and changes over time, the fate of the universe could be different. Some theories suggest that dark energy could weaken over time, allowing gravity to take over and causing the universe to eventually slow its expansion. If this happens, the universe might enter a period of deceleration, and ultimately it could collapse back in on itself in a big crunch. In this scenario, galaxies, stars, and all matter would be drawn toward a single point, and the universe would be reborn in another Big Bang. For now, the mystery of dark energy remains unsolved, but scientists continue to gather data and refine their theories. New observational tools such as the James Webb Space Telescope and the Euclid satellite are helping astronomers to probe the nature of dark energy more deeply. These instruments will allow scientists to study the expansion of the universe with greater precision, helping to answer some of the most fundamental questions about dark energy and its role in the cosmos. As we venture further into the unknown, dark energy continues to challenge our understanding of the universe. It is a force that we cannot see, touch, or directly measure, yet it holds the key to the universe's expansion and its ultimate fate. Whether dark energy is a constant force or a dynamic field, its influence on the cosmos is undeniable. Understanding dark energy will not only shed light on the future of the universe, but will also reveal profound truths about the nature of space, time, and the very fabric of reality itself. As we continue to explore the mysteries of dark energy, we are reminded that the universe is far stranger, more mysterious, and more awe-inspiring than we could have ever imagined. The discovery of dark energy fundamentally altered the course of cosmological research, but it also raised a new set of questions that had profound implications for our understanding of the universe. As scientists began to unravel the mysteries of the cosmos, they uncovered yet another curious discrepancy that could potentially shake our understanding of the universe's rate of expansion: the Hubble tension. This mysterious discrepancy between measurements of the universe's expansion rate has sparked intense debate and prompted a search for deeper, more fundamental truths about the nature of the cosmos. The Hubble constant is the rate at which the universe is expanding, essentially how fast galaxies are moving away from one another as space itself stretches. It is a critical value for understanding the size, age, and future of the universe. For decades, scientists have worked to measure the Hubble constant with increasing precision, but recently two different methods have yielded conflicting results. These different results have been dubbed the Hubble tension, and they have led cosmologists to question whether there is something fundamental that we still don't understand about the nature of space, time, or the forces governing the cosmos. To understand the Hubble tension, let's first take a look at how the Hubble constant is determined. One of the most common methods involves observing the cosmic microwave background, CMB radiation. The CMB is the faint afterglow of the Big Bang, providing us with a snapshot of the early universe when it was just 300. By studying the patterns of this radiation, scientists can infer a wealth of information about the universe's composition, including the amount of matter, and dark energy present, as well as the overall curvature of space. Using the CMB, scientists have determined the Hubble constant to be about 67.4 kilometers per second per megaparsec, kilometers MPC. This value comes from observations made by the Planck satellite, which mapped the CMB in unprecedented detail. However, this result is not the only measurement available. Another method for measuring the Hubble constant involves observing the local universe, the galaxies and stars that are relatively close to us. This method involves using standard candles, such as Cepheid variable stars and type Ia supernovae, whose intrinsic brightness can be calculated. By measuring how bright these objects appear from Earth, scientists can determine their distance, and by measuring their redshift, their velocity. From this, they can calculate the rate of expansion of the universe in the present day. When scientists used this method, they found a value of about 73 kilometers MPC for the Hubble constant, which is significantly higher than the value obtained from the CMB. This discrepancy between the two methods has created a major puzzle in cosmology. If the expansion rate is different depending on whether you look at the early universe via the CMB or the present-day universe via local measurements, it suggests that something is amiss in our understanding of the universe's expansion. The question then becomes, why is there such a discrepancy? Could it be that there is something wrong with one of the measurement methods, or could it point to something deeper? Could this tension be a sign that there is something missing in our cosmological model, perhaps a force or interaction that we haven't accounted for? Several possibilities have been proposed to explain the Hubble tension, but none have been definitively proven yet. One possibility is that the discrepancy could arise from an error in the measurements of either the CMB or the local universe. Perhaps there is some systematic error in one of the methods that has led to an incorrect value for the Hubble constant. Scientists are working to carefully scrutinize each of the measurements to determine if this is the case. However, the disagreement between the two values is so significant that it seems unlikely that a simple error could account for it. Another possible explanation for the Hubble tension is that there could be new physics at play. Perhaps the cosmological model that we currently rely on, the lambda-cold dark matter LCDM model, is incomplete, and there are unknown factors that are influencing the rate of expansion in ways we haven't yet considered. One possibility is that the universe underwent some kind of phase transition in its early history, leading to changes in the behavior of dark energy or the interaction between matter and radiation. Such a phase transition could have affected the rate of expansion in ways that we currently do not understand. One intriguing possibility that has gained attention in recent years is the idea that dark energy might behave differently than we think. The LCDM model assumes that dark energy is a constant force represented by the cosmological constant driving the accelerated expansion of the universe. However, some theories suggest that dark energy could be more complicated than a simple constant. One such theory is quintessence, which proposes that dark energy is a dynamic field that evolves over time rather than remaining constant. If this were the case, it could explain some of the discrepancies in our measurements of the Hubble constant, as the rate of expansion would have changed over time. Similarly, some physicists have suggested that the nature of dark matter might be more complex than we realize. While we know that dark matter exists and plays a crucial role in shaping the structure of the universe, we don't know exactly what it is. Could it be that the properties of dark matter change over time, or that it interacts with other forces in ways we don't fully understand? If so, this could affect the way galaxies move and the rate at which the universe expands, leading to discrepancies in the measurements of the Hubble constant. Another possibility is that there could be new particles or forces that influence the expansion of the universe. In recent years, several new theoretical particles have been proposed that could account for discrepancies in our cosmological models. For example, some theories suggest the existence of sterile neutrinos, hypothetical particles that would interact very weakly with normal matter. If sterile neutrinos exist, they could affect the way matter behaves on cosmic scales, potentially influencing the expansion rate of the universe. The Hubble tension has also raised questions about the fundamental assumptions we make when measuring the expansion of the universe. For example, the LCDM model assumes that the expansion of the universe is uniform and isotropic, that is, the same in all directions and at all points. However, some researchers have pointed out that there could be local variations in the expansion rate. Perhaps the universe is expanding more rapidly in some regions than others, and the discrepancy arises from the fact that we are measuring different regions of space. If this is the case, it could have profound implications for our understanding of the large-scale structure of the universe. Ultimately, the Hubble tension challenges our understanding of the universe and suggests that there may be more to the cosmos than we currently realize. While the two measurements of the Hubble constant are not yet definitively resolved, they point to the possibility of new physics that could change our understanding of the universe on the grandest scales. As new technologies and observational tools, such as the James Webb Space Telescope and the Euclid satellite, continue to push the boundaries of what we can observe, we may soon have the answers to these questions. The resolution of the Hubble tension will likely mark a pivotal moment in cosmology, opening the door to new discoveries and helping to refine our models of the universe. In the meantime, the Hubble tension serves as a reminder of the complexity and mystery of the cosmos. Despite all the progress we've made in understanding the universe, we are still left with deep questions that challenge our assumptions and force us to confront the limits of our knowledge. The search for answers to the Hubble tension will no doubt drive the next generation of cosmologists, physicists, and astronomers as they strive to unlock the secrets of the universe and uncover the fundamental laws that govern its expansion and evolution. Whether the resolution of the Hubble tension reveals new physics, new particles, or new forces, it will undoubtedly reshape our understanding of the cosmos and our place within it. As we continue to explore the cosmos and unravel the mysteries of the universe, one question looms larger than all others. What will happen to the universe in the distant future? Will it continue to expand forever, growing colder and emptier with each passing eon, or will it ultimately collapse back in on itself, in a cataclysmic event that rewinds the cosmic clock? These two opposing scenarios, known as the Big Freeze and the Big Crunch, represent the most widely discussed possibilities for the universe's ultimate fate. While we may not yet know for sure which one will prevail, what is certain is that the future of the universe will be profoundly shaped by the mysterious forces that govern its expansion, particularly dark energy. The concept of a cosmic endgame is not a new one. As early as the 20th century, cosmologists had considered the possibility that the universe might eventually reach a state where it could no longer sustain the cosmic activities that make it so rich and dynamic today. The idea of a heat death of the universe where everything reaches a uniform temperature and no more meaningful processes can occur had been hypothesized as a potential end. But with the discovery of dark energy and the unexpected acceleration of the universe's expansion, scientists began to realize that the end of the universe could be far stranger, more complex, and more unsettling than previously imagined. The most widely accepted scenario today for the ultimate fate of the universe is the Big Freeze, a gradual, irreversible cooling of the cosmos. As it continues to expand, the Big Freeze scenario is largely driven by the influence of dark energy, the mysterious force that's accelerating the expansion of the universe. Dark energy is causing the fabric of space itself to stretch at an ever-increasing rate, pushing galaxies, stars, and even individual atoms farther and farther apart. As the universe continues to expand, the distances between galaxies will grow larger, the rate of cosmic activity will slow, and eventually the universe will become an increasingly empty, cold place. In the early stages of this process, the universe will continue to undergo significant changes. Stars will burn out over billions of years, and their remnants, white dwarfs, neutron stars, and black holes, will slowly fade into darkness. The remaining galaxies will continue to drift further away from each other, as the expansion of space outpaces their ability to interact with one another. Over time, galaxies that are currently part of our local group, including the Andromeda Galaxy, will be separated by vast stretches of space. The gravitational forces that bind them together will be insufficient to prevent them from drifting apart as the universe's expansion accelerates. Eventually, these galaxies will be isolated from each other, and the universe will become a vast expanse of dark, empty space. The remaining stars and other luminous objects will gradually exhaust their fuel, leaving behind dark remnants that no longer shine. The supernovae that mark the death of massive stars will become increasingly rare, and black holes, those enigmatic cosmic objects with immense gravitational pull, will be the last vestiges of cosmic activity. But even black holes won't last forever. Over incredibly long timescales, they will slowly lose mass through a process known as Hawking radiation. This radiation, predicted by physicist Stephen Hawking, results from quantum effects near the event horizon of black holes and causes them to emit energy. Over trillions of years, this process will cause black holes to shrink and evaporate, eventually disappearing entirely. At this point, the universe will enter a state of maximum entropy. The second law of thermodynamics dictates that systems will move toward a state of higher entropy, or disorder, over time. In the case of the universe, this means that energy will become increasingly spread out, and the universe will reach a state where no significant thermodynamic processes can take place. Without the energy needed to sustain life or to drive stellar processes, the universe will be essentially dead, devoid of stars, galaxies, and meaningful interaction. While this scenario might sound bleak, it's important to note that the Big Freeze won't occur for many billions of years. The universe is currently about 13.8 billion years old, and it will take far more time for the processes leading to the Big Freeze to unfold fully. But even so, the idea of an endlessly expanding, increasingly isolated universe is an unsettling one. It suggests that all the richness and complexity of cosmic life, stars being born, galaxies colliding, and new worlds forming, will eventually grind to a halt, leaving only a vast and empty expanse. The Big Freeze is just one possible scenario, but it is currently the most likely given our understanding of dark energy and cosmic expansion. The evidence supporting this theory comes primarily from the observation that the universe's expansion is accelerating. This discovery, made in the late 1990s, was a game-changer for cosmology. Before that, scientists assumed that the expansion of the universe would gradually slow down due to the gravitational pull of matter. But in 1998, two teams of astronomers studying distant supernovae found that the universe's expansion was actually speeding up, not slowing down. This led to the conclusion that there must be some force, which we now call dark energy, causing the expansion to accelerate. The Big Freeze scenario is also supported by measurements of the cosmic microwave background, CMB radiation, which provides a snapshot of the early universe. The CMB shows that the universe is flat and homogeneous on large scales, meaning that the expansion is proceeding uniformly and that there's no sign of a force that would cause the universe to collapse in on itself. This evidence strongly suggests that the expansion of the universe will continue indefinitely, driven by dark energy. However, there is still some uncertainty about how dark energy will behave in the future. Most current models assume that dark energy is a constant force, but it's also possible that its strength could change over time. Some theories propose that dark energy could weaken, allowing gravity to take over and eventually causing the universe to slow down and collapse in a big crunch. This scenario is the opposite of the Big Freeze, where the universe would contract instead of expanding, ultimately leading to a reversal of the Big Bang in a dramatic cosmic implosion. However, based on current observations, the idea of a big crunch seems increasingly unlikely, as the expansion of the universe shows no sign of slowing. Another possibility is that the universe could experience a big rip, a scenario in which the expansion of the universe accelerates so rapidly that even galaxies, stars, planets, and atoms are eventually torn apart. In this scenario, dark energy would grow stronger over time, overcoming all other forces in the universe, including gravity, and causing everything to disintegrate. The Big Rip would mark the ultimate end of all cosmic structures, as space itself would tear apart the very fabric of reality. While this scenario is more speculative than the Big Freeze, it's an idea that has been explored by cosmologists as a potential outcome if dark energy behaves in unpredictable ways. The Big Freeze remains the most plausible scenario for the universe's ultimate fate, but it's important to note that even this scenario is not inevitable. The future of the universe depends on many factors that we are still working to understand. Dark energy, the mysterious force driving the accelerated expansion, could evolve in ways we don't currently predict. The discovery of new forces, particles, or interactions in the distant future could dramatically change our understanding of the universe's evolution. As we look to the future, one thing is certain: the universe will continue to evolve in ways that are beyond our current comprehension. Whether it expands forever, contracts, or tears itself apart, the end of the universe will be shaped by the forces and laws of nature that govern it. The story of the universe's fate is not just a story of cosmic events, it is also a reminder of the transient nature of existence. The universe is not eternal. Its evolution, its birth, and its eventual death are all part of the same cycle that governs everything in the cosmos. In the meantime, We continue to study the universe, driven by the curiosity and desire to understand not just where we came from, but where we're headed. Whether the universe ends in a big freeze, a big crunch, or a big rip, it is a testament to the incredible journey that our universe has taken, from the explosive birth of the Big Bang to the unimaginable future that awaits it. The universe is ever-changing, and as we explore the depths of space, we are reminded that our place in the cosmos is fleeting, yet infinitely precious. As our understanding of the universe continues to evolve, one of the most mind-boggling and exciting possibilities that arises from our studies is the concept of a multiverse. For centuries we have thought of the universe as the only reality, the all-encompassing expanse of space and time. But over the past few decades, new theories and discoveries have suggested the possibility that our universe is not the only one, but rather just one of many parallel universes, each with its own set of physical laws and properties. The idea that our universe is part of a vast and potentially infinite multiverse is both thrilling and deeply unsettling. It opens the door to an entirely new realm of possibilities, challenges our understanding of what reality is, and could fundamentally alter the way we perceive our place in the cosmos. The concept of the multiverse is not a new one. It has its roots in theoretical physics, particularly in the realm of quantum mechanics and cosmology. One of the first ideas to hint at the possibility of multiple universes comes from the many worlds interpretation of quantum mechanics. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, is famously strange and counterintuitive. In the quantum world, particles can exist in multiple states at once, and only when they are measured or observed do they collapse into a single definite state. This phenomenon is known as superposition. The many worlds interpretation proposes that when a quantum event occurs, all of the possible outcomes happen, but in different parallel realities. In this view, every time a quantum event occurs, say an electron passing through a barrier, every possible outcome branches off into its own universe. This means that for every decision, every measurement, every quantum interaction, the universe splits into multiple versions of itself, each representing a different outcome. If true, this would imply that there are an infinite number of universes, each with a different version of reality, where every possible history and future exists simultaneously. The idea of many worlds is a fascinating one, but it's just one of many ideas that have been proposed to explain the existence of a multiverse. Another key idea comes from cosmic inflation, the theory that the universe underwent a period of extremely rapid expansion just after the Big Bang. During inflation, the universe grew exponentially in size in a fraction of a second, stretching space itself by enormous amounts. This theory, proposed by physicist Alan Guth in the 1980s, has been supported by a wealth of observational evidence, including the cosmic microwave background radiation and the large-scale distribution of galaxies. In the context of inflation, the concept of a multiverse arises from the idea of eternal inflation. In this model, the rapid expansion that occurred in the early universe didn't stop everywhere at once. Instead, some regions of space continued to inflate while others slowed down and formed the universe we know today. This means that there are vast, infinite pocket universes, each with its own unique properties, that are continuously being created as inflation continues in different parts of space. Each of these universes could have different physical laws, constants, and even dimensions of space and time. The universe we live in could be just one of many bubbles in a vast cosmic foam, each one representing a separate, distinct universe. The idea of eternal inflation has profound implications for our understanding of the universe. It suggests that the universe we see is not a one-time event, but part of an ongoing, never-ending process of creation. This is where the concept of the multiverse becomes truly mind-bending. If eternal inflation is correct, then our observable universe is just a tiny speck in a much larger, ever-expanding collection of universes. In this framework, there is no reason to believe that our universe is special or unique. Instead, it's just one bubble in an infinitely larger cosmic landscape. But what does this mean for our understanding of reality? The implications of the multiverse are profound and far-reaching. First and foremost, it challenges the very idea of what a universe is. In our everyday experience, the term universe refers to everything that exists, the sum of all space-time, matter, and energy. But in the context of the multiverse, our universe is just one of many. It's a humbling thought. We, as human beings, are but one tiny part of an infinite cosmic landscape of reality. Each of these universes could be radically different from our own, with completely different physical laws, constants, and even the potential for life to exist in entirely unfamiliar forms. Moreover, the multiverse theory raises intriguing questions about the nature of the laws of physics. In our universe, the laws of physics seem to be finely tuned to allow the existence of stars, planets, and life. If the constants of nature, such as the strength of gravity, the mass of elementary particles, and the rate of cosmic expansion were even slightly different, life as we know it could not exist. Some scientists have pointed out that the apparent fine-tuning of the universe for life suggests the possibility of a multiverse, where different universes have different physical laws. In such a scenario, our universe could simply be one that happens to have the right conditions for life to arise. Other universes in the multiverse may have completely different laws of physics, and therefore could not support life as we understand it. This idea is known as the anthropic principle, which states that the universe must be compatible with the existence of observers like us, because if it weren't, we wouldn't be here to observe it. Another fascinating possibility is that the multiverse could explain some of the deepest mysteries of physics. For example, the question of why certain constants in the universe, like the mass of the electron or the cosmological constant, have the values that they do. In a multiverse, these values could be the result of a selection process, where different universes have different values for these constants, and we just happen to live in one where they allow for the formation of life. The multiverse could also help to resolve other major puzzles in physics, such as the fine-tuning of the universe, the hierarchy problem in particle physics, and the nature of dark matter and dark energy. If these phenomena are the result of multiple universes with different properties, it could open up entirely new areas of inquiry and challenge our understanding of the fundamental forces of nature. The idea of a multiverse is not without its critics, however. Many physicists argue that the concept is untestable and therefore not a valid scientific theory. Since we have no direct evidence of other universes, and we are currently unable to observe them, some scientists question whether the multiverse is a scientific hypothesis at all, or if it's just a philosophical idea. After all, a key principle of science is that theories must be testable and falsifiable. Without the ability to test the existence of other universes, the multiverse theory remains speculative. Nonetheless, the multiverse has captured the imagination of scientists, philosophers, and the public alike. It challenges our fundamental assumptions about reality and forces us to reconsider the nature of existence itself. It also raises fascinating questions about the nature of life, the meaning of existence, and our place in the cosmos. If the multiverse is real, then the universe we inhabit is just one of many, each with its own unique properties and possibilities. But perhaps the most profound implication of the multiverse is that it suggests that we are not alone in the vastness of reality. If there are infinite universes, each with different physical laws, it's possible that some of these universes could support life in ways that we can't even begin to imagine. There could be civilizations out there existing in parallel universes with completely different experiences and understandings of existence. The idea of the multiverse implies that we are part of something far larger and more complex than we can ever truly understand. As our understanding of the universe continues to evolve, the multiverse theory challenges the boundaries of science, philosophy, and imagination. Whether it turns out to be true or not, the idea that our universe is just one of many is a profound and humbling thought. It reminds us that the cosmos is far stranger, more complex and more mysterious than we could have ever imagined. The concept of the multiverse invites us to consider not only the nature of the universe we live in, but also the vast potential of all the other realities that could exist beyond our own. It's a thought that pushes the limits of our understanding and leaves us pondering the infinite possibilities of existence. The universe we know today is a vast dynamic entity, filled with galaxies, stars, and planets, all moving and interacting within a fabric of space-time. But the more we explore and understand the cosmos, the more we realize that the universe we can observe is just the tip of the iceberg. Beyond the galaxies, stars, and cosmic structures that we can see with telescopes, there may be realms and phenomena that are completely outside the reach of our current technology and comprehension. These hidden corners of the universe raise questions about the very nature of reality and the limits of our understanding. One of the most exciting and speculative ideas in modern cosmology is the possibility that our universe is just one of many in an ever-expanding multiverse, a vast cosmic landscape of parallel universes, each with its own set of laws, constants, and possibilities. The idea of the multiverse has profound implications for our understanding of the cosmos, and perhaps more importantly, our place within it. If the multiverse theory holds true, then we are not alone in the universe. Rather, we may be one of many intelligent civilizations scattered across different realities. Our universe, with its unique physical laws, constants, and structures, could be just one bubble in an infinite ocean of universes, each with its own history, its own rules, and its own potential for life. This possibility fundamentally challenges our understanding of space, time, and existence itself, urging us to reconsider the very nature of reality. The multiverse theory is not a single unified idea, but rather a collection of different models, each with its own take on the possibility of parallel universes. The first idea to bring the notion of a multiverse into mainstream scientific discourse came from the field of quantum mechanics. Quantum mechanics is the branch of physics that governs the behavior of particles at the smallest scales, where classical mechanics and intuition break down. It is famously strange, with phenomena like superposition, where particles can exist in multiple states at once, and entanglement, where particles become linked in such a way that their properties are instantaneously correlated, regardless of distance, defying our everyday understanding of the world. In the 1950s, physicist Hugh Everett proposed what is known as the many worlds interpretation of quantum mechanics. According to this interpretation, every time a quantum event occurs, such as the measurement of a particle's position or velocity, the universe splits into multiple parallel realities, with each possible outcome of the event occurring in a different branch of the universe. In other words, every time a decision or interaction is made at the quantum level, the universe branches into a new version of itself, where each possible outcome of the event is realized in a separate parallel universe. This idea suggests that there could be an infinite number of universes, each with a different history, different decisions, and different versions of reality. While the many worlds interpretation provides a tantalizing glimpse into the possibility of a multiverse, it is far from the only theory. The idea of the multiverse is also deeply tied to the theory of cosmic inflation, which was first proposed by Alan Guth in the 19th. Cosmic inflation is the idea that in the moments immediately following the Big Bang, the universe underwent an incredibly rapid period of expansion, growing exponentially in size in a fraction of a second. This theory has been widely accepted cosmologists because it explains several key features of the universe, such as its large-scale homogeneity and the uniform distribution of galaxies across vast distances. However, the theory of inflation has an even more intriguing implication: the possibility of eternal inflation. In this model, the universe is not a single isolated entity, but rather a vast and ever-expanding landscape of pocket universes. According to the theory, after the initial burst of inflation, some regions of space slowed down and formed the universe we observe today, while other regions continued to inflate at an accelerated rate, creating new universes with different properties. These new universes, or pocket universes, are constantly being created as inflation continues in different regions of space, leading to a multiverse, a cosmic foam of infinitely many universes, each with its own set of physical laws and constants. In this model, the universe we live in is just one bubble in an endless sea of other bubbles, each representing a distinct universe with its own unique properties. Some of these universes could be radically different from our own, with different laws of physics, different fundamental constants, and perhaps even entirely different forms of life. Some universes may have the same laws as ours, but with slight variations, such as different values for the speed of light or the strength of gravity. Others may have entirely different structures, where dimensions of space and time behave in ways that are completely alien to us. The possibility that we live in such a vast multiverse, where each bubble universe has its own set of rules, challenges our understanding of reality, and raises profound questions about the nature of existence. The concept of eternal inflation and the multiverse also raises the possibility of parallel realities, universes that coexist alongside our own, each with its own version of history. This idea is often depicted in science fiction, where characters might travel between different dimensions or parallel worlds, each with its own version of events. In some ways, the many worlds interpretation of quantum mechanics and the idea of eternal inflation offer a scientific framework for this kind of parallel reality. If these theories are correct, then every possible version of history, every possible choice and every possible outcome might exist in a different universe, with each of us living out different lives in different branches of the multiverse. These parallel universes could be similar to our own, with only subtle differences, or they could be radically different, with completely different laws of physics and structures of matter. One of the most fascinating implications of the multiverse is the question of life in other universes. If the multiverse theory is correct, then life in some form could exist in other universes with different laws and constants. Imagine universes where the fundamental forces of nature are different, where the speed of light is faster, or where gravity is much stronger or weaker. These changes could create entirely different conditions for life to evolve, and we might encounter forms of life that are utterly unlike anything we can imagine. Perhaps there are universes with life forms based on silicon instead of carbon, or even universes where life does not rely on chemistry as we understand it. The potential for alien life in the multiverse is truly limitless, and it forces us to expand our thinking about what life could be. Despite the excitement that the multiverse theory generates, it also presents significant challenges. The most pressing of these challenges is that the multiverse by its very nature may be unobservable. If other universes exist beyond our own, how could we possibly detect them? After all, the multiverse hypothesis posits that these universes are completely separate from our own, and that the space between them is not connected in any way that we can observe. The multiverse, in this sense, may be inherently unobservable and untestable, which raises the question of whether it even qualifies as a scientific theory. A fundamental principle of science is that theories must be testable and falsifiable, meaning that there must be some way to gather evidence that could confirm or disprove the theory. Since we have no way to observe or interact with other universes, some critics argue that the multiverse is more of a philosophical idea than a scientific one. Despite these challenges, the multiverse theory has captured the imagination of physicists, cosmologists, and philosophers alike. It forces us to confront some of the deepest questions about the nature of existence and our place in the cosmos. If the multiverse exists, then we are part of something far larger and more complex than we could have ever imagined. Our universe, with its unique properties and laws, could be just one of an infinite number of universes, each with its own version of reality. This idea is both humbling and awe-inspiring, as it suggests that the universe we know is not the only one, and that reality, as we understand it, could be just one chapter in an infinitely larger story. As we continue to probe the deepest corners of the cosmos and develop new theories of physics, the multiverse will remain one of the most tantalizing and speculative ideas in modern science. Whether or not it is ultimately proven to be true, the very possibility of the multiverse challenges the limits of human understanding and opens the door to new realms of exploration and discovery. It reminds us that the universe, perhaps even the entire cosmos, is far stranger, more mysterious, and more extraordinary than we can ever fully comprehend. And who knows, perhaps in the future, we will find a way to peer beyond the boundaries of our universe and into the infinite, ever-expanding expanse of parallel realities that could be waiting just beyond the horizon of our understanding. The mysteries of the universe are vast, and each discovery only seems to open the door to more profound and enigmatic questions. As we've seen throughout the study of cosmic expansion, dark matter, dark energy, and the potential of the multiverse, the universe is a place of incredible complexity. One of the most perplexing aspects of the universe is not just its structure, but the very process by which it has come to be as it is today. How did the galaxies, stars, and even the very laws of physics come to be what they are? And more importantly, could the universe have once been different, or might it be changing in ways we can't yet fully comprehend? To explore these questions, we turn to the idea of cosmic mergers, collisions, and universe-forming processes that have shaped the structure of the cosmos. At the very heart of the universe's evolution lies the remarkable concept of cosmic growth, not just through the ongoing expansion of space, but through dramatic events that lead to the formation of stars, galaxies, and large-scale structures like galaxy clusters. It is within this context of cosmic evolution that we can explore the possibility that universes themselves might merge or interact, giving rise to new cosmological events. Could the collision of two universes lead to the birth of a new cosmos? Or might our universe be the result of such a cosmic merger in the distant past? The collision of universes. The idea that universes might collide or merge is deeply rooted in both theoretical physics and speculative cosmology. While the multiverse theory suggests that many universes might exist with varying physical laws, the possibility of them interacting is still largely hypothetical. However, there are theoretical models that suggest such interactions are not only possible, but could be a natural outcome of the fundamental nature of space-time itself. One possible model for these interactions comes from the concept of brane cosmology, which arises from string theory and its higher dimensional frameworks. In this model, our universe is thought to be a brane, a three-dimensional object embedded in a higher dimensional space. Brain cosmology posits that our universe, along with others, might exist as separate brains in a higher dimensional bulk. These brains could theoretically collide with each other, leading to significant events, such as the creation of new universes or the reshaping of existing ones. In the case of such a brain collision, the results could be far-reaching. A cosmic collision of two brains, for example, could lead to an intense release of energy, potentially creating the conditions necessary for a new Big Bang-like event, where the fabric of space-time itself would be disturbed, giving rise to a new universe or a transformation of the existing one. The energy released in such a collision could have profound effects on the laws of physics in the resulting universe, potentially altering fundamental constants or introducing new forces of nature. This idea of brain collisions as a mechanism for creating universes also suggests that the boundary between universes might not be as clear-cut as we once thought. In this framework, the edge of our universe might not be the edge at all. It could be just one part of a much larger cosmic continuum where different universes are constantly interacting, colliding and merging with one another in ways that we do not yet fully understand. Merging galaxies and the creation of new cosmic structures. On a smaller scale, the concept of mergers is already a central part of our understanding of how galaxies and other cosmic structures form. The collision and merging of galaxies is not only a common event in the universe, but is also one of the key mechanisms by which galaxies evolve over time. Our own Milky Way galaxy, for instance, is on a collision course with the Andromeda Galaxy, and this merger is expected to occur in about 4.5. The result of such a galactic collision will likely be the formation of a new, larger galaxy, potentially with an entirely different structure than either of its progenitors. These mergers between galaxies have a profound impact on the dynamics of their constituent stars, gas and dark matter. When two galaxies collide, their stars typically pass by one another due to the vast distances between them. However, the gas clouds and dark matter within these galaxies interact more directly, often triggering the formation of new stars as the gas is compressed and heated. This process, known as starburst activity, can lead to a sudden surge in star formation, reshaping the structure of the newly merged galaxy. In addition to the creation of new stars, the merging of galaxies also has significant effects on the supermassive black holes at their centers. Most large galaxies, including the Milky Way, harbor supermassive black holes at their cores, and when galaxies collide, their central black holes may eventually spiral toward each other and merge. This collision of supermassive black holes is one of the most energetic events in the universe, producing intense gravitational waves, ripples in space-time that carry immense amounts of energy. These waves are detectable by instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, which have already made significant discoveries of black hole mergers. These galactic mergers and the formation of new cosmic structures also play a key role in the evolution of the universe on a larger scale. The process of galaxy formation and the growth of supermassive black holes are intimately tied to the expansion of the universe and the distribution of dark matter. As galaxies merge and grow, they exert gravitational forces that pull other nearby galaxies toward them, creating galaxy clusters, massive structures that contain hundreds or even thousands of galaxies bound together by gravity. These clusters are some of the largest structures in the universe and serve as a focal point for the distribution of dark matter. The interactions and mergers that occur within these clusters help to shape the large-scale structure of the cosmos. Could the universe itself be part of a larger structure? While the merging of galaxies and the creation of new cosmic structures is a well-understood process in astrophysics, the idea of universes merging is far more speculative. However, there are a few intriguing models that suggest the possibility of a larger, interconnected cosmic structure in which universes interact with one another in ways we haven't yet fully explored. One possibility that has been proposed involves the concept of a cosmic landscape, a vast multiverse-like space where multiple universes coexist, and each universe's properties are determined by different configurations of fundamental forces and constants. In this model, universes could merge or interact in a way that leads to the creation of new hybrid universes, or could trigger cosmic events that have wide-reaching effects on the evolution of the multiverse as a whole. This kind of interaction between universes could also involve the exchange of energy or information across different regions of the multiverse, leading to phenomena that seem to violate the rules of physics as we understand them. The idea that our universe could be part of a much larger, interconnected structure of universes suggests that our reality may not be the only one. Rather, it is a small part of a much grander cosmic narrative. implications for the future of the universe. If the notion of universe mergers or the possibility of cosmic interactions holds any weight, it has profound implications for our understanding of the ultimate fate of the universe. Currently, the most widely accepted scenarios for the end of the universe are the Big Freeze or Big Crunch. However, if universes can merge or collide, the future of the cosmos may not be as predetermined as we once thought. The collision of two universes could, in theory, result in the creation of a new universe or a dramatic shift in the laws of physics, resulting in a completely different reality from the one we know today. This idea adds another layer of mystery to the study of cosmic evolution. What if the universe we inhabit has already experienced collisions or transformations in the past that altered its course, just as galaxies collide and transform into new structures over time? Could our universe itself have undergone a rebirth from the collision of different universes? And could it be destined to merge again in the distant future? These are questions that challenge the very foundations of cosmology and force us to rethink our understanding of the universe's past and future. Even if we cannot yet observe or test the idea of universe mergers, the very possibility challenges the boundaries of our imagination. It forces us to confront the potential for cosmic interactions on scales that are beyond our current comprehension, suggesting that the universe may be more fluid, more interconnected, and more dynamic than we ever realized. Whether through the merging of galaxies, the creation of new cosmic structures, or the speculative idea of universe interactions, the universe is far more complex than we can grasp in our current scientific understanding. As we continue to explore the cosmos and develop new theories and technologies, the concept of cosmic mergers and the interconnectedness of universes serves as a reminder that our universe is not isolated or static. It is part of an ever-changing, ever-expanding fabric of reality, one that is still full of unknowns and surprises. The future of the universe, and perhaps even the very nature of reality itself, remains as mysterious and awe-inspiring as the stars in the night sky. As we peer deeper into the universe, we come face to face with one of the most astonishing questions of all. Could the universe itself be a living, evolving entity? What if the very fabric of space-time is more than just a static stage for cosmic events, but an active, dynamic process capable of adaptation, change, and perhaps even conscious involvement in its own evolution? This idea might sound like science fiction at first, but recent developments in cosmology, quantum mechanics, and even philosophy have led to new perspectives on the nature of the universe, suggesting that its true nature could be far more intricate and alive than we have ever imagined. To explore this concept, we need to first recognize that the universe is not merely a collection of stars and galaxies floating in a vast emptiness. It is a complex, interconnected system, where everything from subatomic particles to the largest structures in the cosmos is governed by the fundamental laws of physics. Yet, what if these laws themselves are not rigid or unchanging, but instead evolve over time, just as organisms evolve on Earth? Could the universe be a self-organizing, self-regulating system, shaped not only by the forces of gravity, dark energy, and quantum mechanics, but by an intrinsic tendency toward growth, complexity, and perhaps even intelligence? This brings us to a concept that has been discussed in the realms of both theoretical physics and philosophy: the idea that the universe may exhibit emergent properties. In physics, an emergent property is a phenomenon that arises from the interactions of simpler components, often in ways that cannot be predicted from the properties of those individual components. These properties emerge when complex systems reach a certain threshold of complexity, and they are not inherent to any single part of the system, but are instead a product of the interactions between its parts. For example, the formation of galaxies, stars, and planetary systems is an emergent property of the interactions between matter, energy, and gravity. These cosmic structures arise not from the simple accumulation of individual particles, but from the intricate dance of forces that govern their behavior. The universe, in a sense, is more than just the sum of its parts. Its complexity emerges from the interplay of fundamental forces, creating new levels of order and organization that were not present in the beginning. But what if this emergent complexity goes further than just physical structures? What if the very laws of physics themselves are emergent, subject to change over time as the universe evolves? This is a radical concept that challenges the idea of fixed, immutable laws governing the cosmos. It suggests that the laws of nature, such as the constants that determine the strength of gravity or the behavior of light, could be in a constant state of flux, adapting to the changing conditions of the universe. This idea is supported by certain cosmological models that suggest the universe might not have always been governed by the same laws we observe today. The possibility that the universe's laws might evolve over time raises profound questions about the nature of reality. Could the universe be alive in a sense, actively changing, adapting, and evolving in ways that we don't fully understand? This idea takes inspiration from the concept of panpsychism, a philosophical view that consciousness is a fundamental feature of the universe, present in all things, even at the most basic level of reality. While panpsychism is traditionally considered a metaphysical idea, recent developments in quantum mechanics and cosmology have made it a more serious consideration. The suggestion that the universe might have a kind of mind or awareness, even if it's not like human consciousness, opens up new possibilities for understanding the cosmos. The concept of the universe as a living, evolving entity also brings us to the question of whether the universe might have a kind of purpose. This idea may seem strange from the perspective of modern science, which typically views the universe as a product of random processes without inherent intention or direction. But if the universe is indeed an evolving, self-organizing system, could it be driven by some underlying principle or purpose? Could there be an intelligence, whether conscious or not, that shapes the universe's evolution toward greater complexity and order? One way to think about this is through the lens of self-organizing systems in nature. In biology, we see countless examples of self-organizing systems, where complex patterns and behaviors emerge from simple rules. From the flocking of birds to the formation of galaxies, these systems can reach a level of organization and complexity that appears to be driven by some intrinsic principle of order. Could the universe itself be a giant self-organizing system, with its evolution guided by some fundamental principle of complexity, just as life on Earth evolves toward greater diversity and complexity? If the universe does indeed follow some kind of self-organizing principle, then perhaps it is more than just a random collection of stars and planets. It could be a system in which the very process of evolution, whether at the level of matter, energy, or even consciousness, is part of a larger cosmic design. This design could be subtle, almost imperceptible, yet still powerful enough to shape the universe's trajectory and lead it toward ever higher levels of complexity. This brings us to another fascinating idea: the possibility of the universe itself being conscious, or at least capable of exhibiting some form of awareness. While this concept may seem far-fetched, it is not entirely outside the realm of scientific speculation. Some physicists, such as the late physicist John Archibald Wheeler, have proposed that the universe itself might have an inherent consciousness that is reflected in the behavior of subatomic particles and the fundamental laws of physics. Wheeler famously coined the phrase "it from bit" to suggest that the physical universe is, in some way, rooted in information. This idea implies that the very fabric of the universe could be based on a form of knowledge or awareness that manifests in the behavior of particles, waves, and even the forces that govern them. The notion of a conscious universe has echoes in ancient philosophical traditions. For centuries, many cultures and belief systems have posited that the universe is not just a collection of matter and energy, but a living, conscious entity. This view is perhaps most famously expressed in the ancient Greek idea of the cosmos, where the universe was seen as an interconnected, harmonious system, imbued with meaning and purpose. In the 20th century, this view was given new life by thinkers such as Carl Jung and Erwin Schrödinger, who suggested that there may be a deep, underlying consciousness that pervades the cosmos, manifesting itself in the physical and mental worlds. But the question of whether the universe could truly be conscious in the way we understand consciousness is still a matter of intense debate. Some argue that the concept of consciousness as we understand it is too complex to be applied to the universe as a whole. Consciousness, after all, is typically thought of as something that arises from the interaction of neurons in the brain, a product of biological evolution. However, others argue that consciousness could be a fundamental feature of the universe, not just a byproduct of brain activity. In this view, consciousness is not limited to individual beings, but is a property of the universe itself, a cosmic awareness that shapes and guides the evolution of the cosmos. Regardless of whether the universe is conscious or not, the idea that the cosmos is a living, evolving entity has profound implications for how we view our place within it. If the universe is a self-organizing, ever-evolving system, then we are not passive observers of the cosmos, but active participants in its ongoing process of growth and transformation. Our actions, our thoughts, and our understanding of the universe are part of the larger cosmic story, contributing to the evolution of the universe in ways we may not yet fully understand. This concept encourages us to view our lives not as isolated events, but as interconnected with the larger processes of the cosmos. In this sense, the universe may not be an indifferent backdrop to our existence, but a dynamic, living entity that is constantly shaping and being shaped by everything within it. As we continue to explore the universe and push the boundaries of our understanding, we may one day find evidence that points toward a more profound, interconnected relationship between consciousness, life, and the cosmos itself. Whether the universe is truly alive or conscious in the way we understand it, the fact that it is capable of such extraordinary complexity and self-organization suggests that it is far more than just a passive, inanimate system. The universe is, in a sense, a living entity, and we, as its inhabitants, are part of its ever-evolving story. In the end, the idea that the universe is a living, evolving entity challenges our traditional understanding of the cosmos and invites us to see it in a new light. It encourages us to consider not only the material components of the universe, but the deeper, more fundamental principles that govern its existence. Whether the universe is conscious or not, the fact remains that it is a place of unimaginable complexity, and it is up to us to continue exploring its mysteries and discovering our place within this ever-evolving, dynamic reality. As we do so, we may find that the universe is not just something we observe, but something that we are actively participating in, contributing to its ongoing growth and transformation. As we reach the end of this exploration into the vast, complex nature of the universe, it becomes increasingly clear that the more we learn, the more we realize how much remains unknown. From the birth of the cosmos in the Big Bang to the mysterious forces of dark matter and dark energy, and the speculative yet tantalizing idea of a multiverse, the universe is a place of boundless mystery, constantly challenging and expanding our understanding. One of the most striking revelations from our journey through the cosmos is the realization that the universe is in a constant state of evolution. It is not static or fixed, but rather a dynamic, expanding entity, subject to the forces of gravity, dark energy, and the fundamental laws of physics that govern its structure. We have come to understand that the universe is not simply a backdrop for the events that unfold within it, but an active, changing participant in its own story. The expansion of space, the formation of galaxies, and the life cycles of stars are all part of an ongoing cosmic process that stretches from the beginning of time to its eventual end. Perhaps the most profound idea to emerge from modern cosmology is that the universe is not just a collection of objects floating in space, but a vast interconnected system where every galaxy, star, and particle is influenced by the forces that shape its evolution. The discovery of dark energy and the accelerating expansion of the universe has radically transformed our understanding of the cosmos, suggesting that the very fabric of space-time is stretching, pushing galaxies farther apart, and driving the universe toward a cold, isolated future. Yet within this vast emptiness, there is still much to explore and understand, new mysteries that promise to deepen our comprehension of the nature of existence itself. At the same time, the speculative ideas surrounding the multiverse and the potential for parallel realities have opened up exciting new possibilities. The notion that our universe could be just one bubble in an infinite ocean of universes, each with its own laws and constants, challenges everything we thought we knew about reality. The implications of such a concept are profound, forcing us to confront the limits of human knowledge and the possibility that the universe is far stranger and more complex than we can even begin to fathom. While we have yet to find concrete evidence for the multiverse, the exploration of this idea pushes the boundaries of physics and philosophy, urging us to think beyond our own cosmic backyard and imagine the unimaginable. Despite these thrilling possibilities, there are still many unanswered questions that continue to shape our quest for knowledge. Could the universe be a living, evolving entity? Could the very laws of physics themselves evolve over time, adapting to the changing conditions of the cosmos? These questions challenge our understanding of life, consciousness, and the fundamental nature of reality. As we continue to probe the deepest reaches of space and develop new theories in quantum mechanics and cosmology, we may find that the universe holds more surprises than we ever thought possible. The journey through these cosmic questions also reminds us of our own place in the vastness of the universe. As we look out into the stars and explore the mysteries of space, we are reminded that we are just one part of a much larger story, a story that spans billions of years and reaches beyond the limits of our current understanding. The universe is both humbling and inspiring. It makes us feel small in the grand scheme of things, but it also invites us to take part in an ongoing adventure of discovery and learning. In the end, what becomes clear is that our exploration of the universe is far from over. Each new discovery, each breakthrough in our understanding of the cosmos, opens the door to new questions and deeper mysteries. The pursuit of knowledge is not just a scientific endeavor, but a profound journey that connects us to something far larger than ourselves. Whether we are studying the farthest reaches of space, contemplating the mysteries of dark energy, or imagining the possibility of other universes, we are participating in a search for meaning that transcends time and space. As we continue to seek answers to the fundamental questions of existence, the universe remains a vast, awe-inspiring frontier filled with endless potential for discovery. Our understanding may be imperfect, but it is a journey worth taking. The universe is a place of mystery, wonder, and infinite possibilities, and the more we explore, the more we come to realize that the answers we seek are just the beginning of an even greater adventure. The future of cosmic exploration holds the promise of uncovering truths about the nature of existence itself, and we as a species are fortunate to be part of this extraordinary journey.